We're talking about vector spaces, purely vectors, n tuples. First, I want to clear up a couple of things when I covered this in the previous video. Say you have a set of vectors that doesn't contain the zero vector. Well, let's look at this test. If you multiply anything in that set by the scalar zero, you're going to get zero, which we just said is not in the set. That's why any vector space must contain the origin. I didn't say that clearly before. But the other thing I wanted to say about this is these things, I want to say these have to go on forever. You have real trouble if you try to cut it off. Let me take the example here. Let's just look at this red plane, which is, I guess, the Z plane. A subset would be just a plane to the right where x is positive. Is that a subspace? Well, if I take any vector in that plane and multiply it by a negative scalar, I'm going to end up over here, which we just said is not in that subset. So that's not a subspace. I want to say they got to go on forever, things like lines and planes. Okay, now let's get into dimension and basis. What is the dimension? To me, the more intuitive way to define it is it's what's the minimum number of vectors required to span the vector space. We're talking about dimension and basis of vector space. What's the minimum number of vectors required to span? That's the dimension. The other way to say it is what's the maximum number of linearly independent vectors in V? Because if you add any more vectors to it, they're not going to be linearly independent because that's the maximum number. Think about that. Then the basis is a set of such vectors. So you'll basis set of vectors, you'll have as many vectors as the dimension of that vector space. Basis vectors will span the whole vector space, and it's the fewest, or they're not unique. Bases are not unique, but it's the fewest number of vectors and span the vector space. That's what we wanted to do. By the way, another anomalous thing about the zero vector, it's not even independent of itself, so its dimension is zero, and its basis, it's an anomaly for lots of things. Let's take an example. Let's see. A and B, we've seen them before. You can generate any point in a plane, in the XY plane. Those two vectors span R2. We call it R2. Real R for real numbers, two-dimensional, an XY plane. So therefore, R2 is a vector space. These two guys are linearly independent. They're not scalar multiples of each other. And since we're only talking about two dimensions in the first place, you can't have more basis vectors than the dimension of your subspace, vector space. So they're linearly independent and they span the whole space. So the dimension of R2, Y plane, is 2, and these are a set of basis vectors for it. In fact, they're called the standard basis. We'll probably see I and J. And generally Rn, n-dimensional real numbers, has a dimension of n, and the standard vectors is, I'll go through this a little bit later, I call it the 1-0 trick. An easy way to set up a bunch of linearly independent vectors is to set one free variable to 1 and the rest to 0 and sequence through them all. So this would be like a basis set for R to the Rn. Here's another example we've seen before. Now B is a scalar multiple of A. which means A and B are not linearly. So the span is just this line, a scalar multiple of 1, 2, or y equals 2x. So they don't span the whole space. What is the dimension is 1. And this right here, 1, 2, is a good enough basis for that vector space. The vector space just has dimension 1. Let's see this for another